right on time. Okay, why don't we get started? Yes, yeah, we can begin. So, hi everyone. We're very pleased to have Jess McIver visiting us today at the CITA seminar. Jess is Canada Research Chair in Gravitational-Wave Astrophysics at UBC. She's the Deputy Spokesperson of the LIGO Scientific Collaboration. She did her PhD work at University of Massachusetts Amherst before doing a postdoc at Caltech and then taking up her position at UBC. And today she'll tell us about new frontiers in gravitational wave astrophysics. So please take it away, Jess.
Thank you very much. Yes, so we're on a journey today. We'll cover aspects of the LIGO detectors. We'll cover an overview of the current observing ground and also some of the challenges that we face in terms of the detector noise that we have, which is my own specialty in my research. I also want to tell you about a really exciting initiative that's being led by a PhD student in my group, Alan Nee. So thinking about the prospects for the first detection of a galactic source of gravitational waves. All right. So here's the current network that we're working with. And so these are the 3 detectors that have been used for gravitational wave observations that have been reported to date. So they're the 2 LIGO detectors in the US, as you may know, and our sister detector, Virgo, which is a 3-kilometer detector in Pisa in Italy. So right now, so we are in the middle of our 4th observing run. It started on May 24th of this past year. We actually just started our commissioning break last week on January 16th. We are have so far only gotten data from the 2 LIGO detectors, and we're hoping that Virgo is going to join us in O4b, which is going to start in the middle of March. So what do we do with this data? So each one of these detectors is issuing a time series, usually noisy data, like you see here in blue. So this is the amplitude of the data over time. And our hope is that buried in this noisy data is some kind of a signal. So here we see a compact binary coalescence. This could be black hole or neutron star. And the way that we can leverage this data is by taking what we know about general relativity. So we also understand that gravitational waves, being very weakly interacting, are going to propagate to us essentially unchanged. They're going to travel through gas, through dust, through the Earth itself, and we are going to get that signature of the source in our detectors on Earth. So we can use this powerful technique called match filtering to compare models of our signals directly to our noise to identify those weak signals. So the way that we do this, we can essentially take the inner product between the model and the signal, and we can do this weighting it by the power spectral density of our detector noise. So let's see what this looks like. So here we're taking our modeled signal, and you might notice if you look really carefully that it's not an exact match for that real signal that's in the data. And here we're just computing this cross correlation, this inner product between the model and the data. And we're going to look here now for a spike, some kind of a registered similarity between the model of our signal and our data. And we can do this for hundreds of thousands of modeled sources. So these are sources spanning the whole range of mass and spin that we expect we might detect with the abilities of our detectors. And this is an older plot, but I really like the way that it breaks it down in color coding in terms of this template bank of modeled signals. So here we've got what we call the primary mass arbitrarily. We're just assuming that mass 1 is going to be heavier than the companion, the secondary mass. And we're populating it all the way up into the intermediate mass black hole range. So current template banks will actually extend even farther beyond 100 times the mass of our sun. And what I want to draw your attention to is these colors representing spin. So here for black holes, so we're allowing the spin to vary in our template bank all the way up to close to the maximal spin. For neutron stars, we make the interesting decision to try and conserve computational power that we're requiring the neutron star to be spinning within the limits that we observe neutron stars in our own galaxy. So this will help us to cover a broader array of what we consider to be the probable parameter space of masses and spins. And currently this is about a million, on the order of 1 million templates. So we perform this exercise with all of our templates over our data. We get this time series that we call an SNR time series, which is again this cross correlation. And our next job, aside from inferring the parameters of these sources is going to be to try and tell how significant each one of those candidate sources are. So there are a number of different ways that you could construct this. One way to construct your backgrounds is called time slides. So here you take that SNR time series that we computed, and you're going to take that for each detector. So let's say we have 3 detectors in our network, and we're going to take those candidates and we're going to slide them in time by a time greater than the gravitational wave travel time, which is roughly about 10 milliseconds. And now we're going to recompute this search for correlations in time, and necessarily, because we've shifted this, any correlations that we find must be due to noise. So we can empirically measure the rate at which noise in our detectors is going to produce an equivalent candidate, which is how we have derived these background curves that you see here. So if I were to have a candidate, I would measure it to have some signal-to-noise ratio. So this is the network signal-to-noise ratio. It's just the quadrature sum of the signal-to-noise ratio in each one of the detectors in my network. And this is, for example, a dashed blue line here. And in order to estimate the significance, I would compare it to the rate at which an equivalent noise event would produce something with a similar network SNR. So there are 2 different background curves here. So background distribution in red is if I don't use anything that I know about my detector status, the behavior of the data, the behavior of the environment, if I come at this totally blind. And the curve that you see here in gray, this is where I use everything that I can determine about my detector. So the performance of the detector and also the noise, and I'm here removing elements of time that I know are highly likely to be producing false triggers. And we'll see some examples of this in just a little bit. So you can see, even for the same candidate, I can dramatically improve its significance. I can dig farther into the noise if I understand about my detector's behavior. All right, so how do we then infer the source properties? So here, we assume that our data is going to be the sum of the signal as seen through the lens of my detector network plus my detector noise. And we make a really key assumption here about the detector noise, which is in the construction of this likelihood that I will input into my Bayesian infrastructure. And we're assuming here that the residual, if I subtract the signal from my noise is going to be Gaussian. This is a really key assumption that we're making. And as we will see later on in the talk, this is not a good assumption to be making. Often the data in the LIGO detectors and the Virgo detector is non-Gaussian, non-stationary, and very ill-behaved. And so folks like me, a lot of our time is spent thinking about how to make this assumption true. But with that assumption, as it stands, we can get good estimates of our source properties because we do understand the behavior of our detectors fairly well. So here's just a snapshot of our previous catalog where we're looking at the effective spin of the system versus the chirp mass. You can see that current detectors, and especially previous measurements, have quite a lot of uncertainty in the spin so far. We'll need more precise data with higher signal fidelity from future observations to do better with kind of constraining spin. And here's a nice example of that. So here, the left hemisphere, this is telling you about the inferred spin of the primary compact object, so the heavier of the two in the binary. And here is the secondary mass. And the distance from 0, so this is from 0 to 1, is telling you about the inferred amplitude of the spin. And then the direction here, so 0 degrees is aligned with the orbit of the system, and 180 degrees is anti-aligned. So you can see that often, this is just one example, but it's representative of the broader trends, that we can get a much better inference about the characteristics of the spin for the primary object, and we get very little information, at least with previous observations on current detectors, generally about the secondary mass. So we'll need improved detectors. All right, so where are we right now? So we mentioned that we're in the middle of the 04 run. So here is the era prior to 2010, when I first started working on LIGO. And we did take a lot of observations. We didn't see anything, but that brought us to 2015. We have the first 3 observing runs where 03 was cut a bit short due to the pandemic. We stopped taking data in March of 2020. And now here we are, right here where this arrow is at the very beginning of this commissioning break in 04. So leading up to 04, so this big break that you see here between the start of COVID-19 and May 24th of this past year. So a lot of improvements were made that helped us to push down that noise floor, including upgrades to the lasers, so they're now capable of inputting more power into the detectors, which will then be circulated up to the order of hundreds of kilowatts in each one of the detector arms. We also have new baffles to combat stray light. So this is one of the most insidious forms of transient noise, because when the light that's reflected away from the main carrier beam hits some shiny surface that's moving, some portion of that light can interfere with the main carrier beam and generates this difference in phase that can actually rise up in frequency. So if you're familiar with gravitational wave data analysis, you'll understand that that's alarming if you've got a noise source that's rising in frequency. So this has been very effective in combating stray light and scattering noise. That's been much reduced from previous runs. We've also replaced some of the test masses to improve the coatings, which has helped us to actually have a lot more stable control of the detectors. We used to need to avoid some very nasty baked-on imperfections in the mirror coatings. And then the biggest change, in my opinion, is this new 300-meter cavity for this frequency-dependent squeezed light. So we have been squeezing lights in previous observing runs. So in 03, this was implemented, and it was effective in pushing down the high-frequency noise. However, it came at a cost, which is an increase, this limitation at lower frequencies. So frequency-dependent squeezing allows us to improve our performance at higher frequencies, and without that cost of introducing those at low frequencies. And what are we doing right now during this 2-month period? So the 2 LIGO detectors are right now in the middle of their commissioning break, focusing on cleaning those optics again to reduce the imperfections on the surface of the mirror, and also still doing some additional mitigation of the scattered light. And again, we're really hoping that the Virgo detector is going to be able to join the second part of the run at roughly about 50 megaparsecs or so. All right, so what does this look like? So I'll show you a snapshot of the detector performance during this observing run so far, so 04A, relative to the previous observing run for each one of the detectors. So this is LIGO Hanford. The previous observing run 03 is in blue. The current observing run 04 is in orange. And you can see a really, really broadband improvement. And a lot of this improvement at higher frequencies comes from improvements in squeezing, also improvement in the circulated power in the arms. At lower frequency here, some of this is coming from this implementation of frequency-dependent squeezing, but also a lot of improvements in the control systems of the interferometer that are helping to mitigate resistance to ground motion. And some quick stats. So they're currently operating at about 370 or so kilowatts of power with about 4 decibels of squeezing. Again, usually having an impact above about 100 hertz or so. And they're at about 150 megaparsecs of range, which is almost to design sensitivity. So the design sensitivity range is about 160 megaparsecs to 185. So we're very close. We're hoping to reach that for Hanford at the end of the commissioning break. All right, so for LIGO Livingston, so here we've got a red curve. This is the end of 03. This blue curve is the start of 04. And then this green curve is a few months into 04 after they'd made some improvements and especially some noise mitigation of some incursions down at the low frequency ends. But you can see the gains that have been made, especially in the increase in power and also improved squeezing at these high frequencies here. By the way, does anybody know what these spikes are in the spectrum?
60 hertz.
Yes, you see 60 hertz, that's right. So that's the AC power grid in North America. Does anybody have a guess for this guy? It's a really tall one.
tension string.
Yes, exactly. This is the mechanical mode of the strings that are holding the mirrors and isolating the mirrors from ground motion. We call them the violin modes, and each one of these lines that you see in harmonics afterwards are also due to the same fundamental harmonic. So these are going to come up later. So when we're looking for galactic sources, we're not as concerned about glitches. So if we're interested in compact objects matching together, then we're thinking a lot about transient noise and glitches in the detector. If we're thinking about a very long duration persistent source that's semi-sinusoidal, it's these kind of features that are going to be most problematic to our search. All right, so here's a snapshot coming back to transient land and compact objects smashing together. So in a mere just over 6 or so months, we have detected confidently 81 total candidates, with many more sub-thresholds, potential candidates, only 11 retractions so far, which is much better than we were doing in '03, so that's very good. So here's a picture. This is the stellar graveyard animation that you may have seen in some other talks, and this is depicting all the compact objects that have been detected with gravitational waves by LIGO and Virgo from the first 3 observing runs. And now here we've just about doubled it. So there are 90 events depicted here from '01, '02, and '03, and now in just the first 6 months of '04, we have almost again as many. And they're dominated so far by what we think are likely binary black holes. So here I'm just quoting the P astro that's reported in the public alert information. So anything above a 50% probability of being a binary black hole is in green. Neutron star black holes are in blue. And then I noted that we've had successful early warning attempts. So who's heard of an early warning search? Okay, this is worth mentioning just because it's really cool. We're not going to spend any time on it, but so unlike a binary black hole signal that will sweep into the sensitive range of the detector and only spend maybe tens or maybe hundreds or so of cycles, it's very short, less than a second generally at higher mass. However, neutron stars now, they will merge at a high enough frequency that they can spend thousands and thousands of cycles in band, so a minute or more, and will do even better than that as detectors continue to improve. But we do have the capability to run that match filter search and build that signal to noise ratio up in advance of the merger. So this is what we mean by early. So we can fairly confidently detect some signals up to tens of seconds in advance of the merger. So we haven't issued a confident detection of early warning, but it's a very cool technology that does exist to inform astronomers. All right, and Canada is playing a huge role in these observations, especially for '04. So Canada is powering over 10% of the total computing infrastructure for LIGO, Virgo, and Kagra. So this is over 2,500 collaborators all around the world. We also have a lot of scientific leadership, including 2 of the folks here at UBC, Maya and Phil, have very key leadership roles within LIGO, Virgo, and Kagra. So Canada also builds our flagship calibration software infrastructure that's called PyDARM, and we're also responsible for the main detector monitoring. So if you ever see images like this, or actually the plots that we were looking at this morning during coffee, are also powered by this same software infrastructure. All right, so all that sounds great. We've detected a lot already. So we're going to go from the land of maybe a simple Michelson interferometer picture towards reality, where we'll need to pay very close attention to the quality of our data in order to be making confident astrophysical inferences. All right, and one of the things we worry about, in addition to the introduction of noise into the data, is how often we can observe. So if you're an astronomer, you're familiar with uptime due to where the sun is in the sky, with the weather. So we're also concerned with the weather, but for very different reasons. So we lose uptime largely driven by ground motion. So weather for us has got a lot to do with what the oceans nearby are doing. So for LIGO Hanford, this is the body of water that's the Pacific Ocean. And for LIGO Livingston, it's the Gulf of Mexico and the Atlantic. And I want us to take a quick look at this and see if we can guess what's happening here, especially for poor Livingston in the last couple of months or so. Any guesses as to what might be causing this reduction in uptime? We're doing our best, by the way, to observe as often as we can. I will point out Hanford suffers from this too a little bit. Not as much, but it does. Yes, the answer is winter. Winter has come. That's exactly right. So when winter does come, so for gravitational wave detectors that are based where they happen to be in the US, that means higher waves. And those higher waves means excited resonances of those bodies of water, and that means what we would call high microseism. And that's a lot of ground sloshing around, especially when your detector's built on top of a swamp. It can be pretty hard to deal with. Another part of the plot that does not happen during winter I want to draw your attention to is here. So are there any guesses for what might be happening to Livingston about this time? Losing a lot of uptime. I think technically speaking it does overlap with hurricane season, but it's not a hurricane. It's a good guess though. We've said weather. This is a human-generated cause, I will say. Has anybody been to Lago Livingston? You should go. It's pretty cool. You will be there, so you'll see exactly what I mean.
Is this, I think I know what this is. Is it logging related?
It is logging related. Very good. All right, so I'll show you this breakdown of what we think is causing a lack of uptime. So whenever we're observing that's shown here in green, anything that you see that's in this kind of yellowy orange color, that means we're trying to what we call lock. That means to get the light resonant in the interferometer, and we're not able to do so. Brown means that this is some known cause of environmental noise that's interfering with our ability to take data. So we've already said that we understand that this part over here, this is due to the weather, this is wintertime, this is fairly normal for the LiDAR detectors. And then over here, this is indeed correlated with logging. And I'll show you what this looks like. But first, given what you understand about gravitational wave detection, so we've got some central laser source that's shown down these two perpendicular arms. It returns to the same beam splitter, and all of our readout equipment is there as well. I just want you to visualize where you think might be the worst possible place for logging to be happening. Just hold this in your mind, and I'll show you where it was happening at this time. Oh yes. Right exactly there. And what this looks like, so if you look at the ground motion monitors nearby at LIGO Livingston, so here, just at about 6 in the morning, every day, Monday to Friday, the trucks would roll in, they'd start leveling trees, they'd be dragging the trees around as they're hauling them out, and we would immediately lose luck. So as soon as that spike jumps up, we're no longer able to take data. We try so that what you're seeing here, these are different states of the interferometer as it's trying to walk up to achieve the nominal observing mode. So there are multiple different cavities that all need to be resonating at the same time. If we lose luck, we have to start over often and get each one of those resonance until finally we're able to take data. Eventually we gave up and rode the rest of the day out in down mode, and as soon as the loggers were done for the day, we were successfully then able to log. But that accounted for quite a number of lost hours for LIGO Livingston. And something else that this ground motion can do is introduce these noise artifacts into the data. So even when we are able to observe when the light is resonant in all of the different optical cavities in the detector, so something that we need to deal with is all of these little dots, which I'll call glitches. So we're looking at the course of a day here. Anything in green means we're observing. Anything in red means that we're not. This doesn't necessarily have to be logging. It could be an earthquake, any number of other technical problems. And each one of the dots that you're seeing here, so the y-axis is frequency, is a burst of power in the data. So these are generally glitches. These are transient noise. And the color here is showing you how loud they are. So how loud is that burst in the data? And these can mask and mimic real sources of gravitational waves. They can add to that background and make it more difficult to detect real sources. They can also obscure the power of a gravitational wave signal. And I'll just zoom in here and just show you how frequent these have been in the past. So this is from an example of open data. Our most recently open period of data was the previous observing around 03. So just to zoom in here on a time scale that's now on the order of seconds. So what's happening here, again, we said that these would rise in frequency, the scattered light. And if you look, these are happening about once every other second. So if you have a real source that's happening during this period of light scattering, it's really quite highly probable that it's going to intersect in some way with one of these bursts of noise. And you have to then disentangle what power is coming from your source and what's coming from the glitch. And we have a whole host of glitches, not only light scattering, we also have, I think the top of this is just a little bit cut off, but I'll read the funny names for you. There's Fringy the Sea Monster is a favorite. You may not be actually able to read some of these titles in the back. What's another good one? Atomti, this is the Swedish gnome hat, I think, is where that name comes from. There's Scratchy, which is supposed to be like a horror movie, Scratch. But we give them fun names. They're extremely problematic. It makes us feel a little bit better about it. But what you're seeing here is the menagerie that was published for this Gravity Spy paper. And Gravity Spy is this extremely successful machine learning algorithm that's been used to classify examples of these glitches. So now instead of a human being saying, I don't know, that happens at about this frequency, let's maybe just take all the glitches at about that frequency and call it a day, and we'll do some characterization that way. Now we have a very effective machine learning algorithm that can run on all glitches, all millions of glitches during an observing run, and return to you examples that are likely to be from that class. So we can do really detailed studies of how these glitches vary as a function of time. We can do associations with, for example, humidity, as was found to be coupled with the blip class. And why would we like to understand these glitches better? So, for example, what we're looking at here, this is the power from a real gravitational wave signal. And something that I recently spent quite a lot of my time on as a leader of the review for the collaboration was thinking about how do we make that Gaussian noise assumption as close to true as possible so that we can do our Bayesian inference as we normally do and recover accurately those source properties. So here was an example where we had some really bleedingly loud scattering arches that were coming pretty close, so within the analysis window for our Bayesian analysis of the source. So the nominal approach that's described in Davis et al. Is that you incoherently model this glitch with wavelets and then subtract it out as best you can. And you'll see that this does a fairly good job if you compare these two plots. However, it does seem to leave some residue that's consistent with Gaussian noise, which is the threshold down to which we would subtract. And we try and understand what kind of an impact not subtracting the noise would have, because this is a very expensive process, both in person power and also in computing power. So it could take, in the past observing runs, something like 4 or 5 months for us to produce a final subtraction for one candidate. So minimizing the amount that we need to do that is a major goal. So one of the projects that Nico Lacoche, who's a PhD student at UBC, is working on is taking a simulated gravitational wave signal, walking this across some data with a real glitch in it, and then looking at how the parameter estimation varies, trying to isolate where the safe regions are in time, where we don't need to worry about subtraction. So that's a major goal of the study. Nico's also working on characterizing whether or not there's some kind of bias that you can use to predict what impact this would have in near real time. So let's say, for example, here we've got the mass of the primary source that tends to be underestimated in this case. A worry that we had is, what if this signal overlapping with a glitch was actually overestimated and it's actually an electromagnetically bright source that astronomers would be interested in following up. So that's one angle. We're also trying to understand impacts, for example, on the sky localization. So let's say we detect one of these in near real time. Are we going to need a new sky map? What is that sky map potentially going to look like in the meantime as that new sky map is being run on mitigated data? All right, another case that I want to share with you is the curious case of 200129. So this is the first report of potential signs of precession. So this is a component of the spin that's not aligned with the orbit of the system. So this is a very subtle feature. It's a very lowest in our feature in the data. This study got a lot of headlines back in 2022, wobbling black hole. And what I want to point out to you was the character of the data itself. So this is the raw data, the original data. And I want you to notice these glitches here. What's happening there is there's a camera shutter in the detector. This was LIGO Hanford. That's going shut, shut, shut. And a little accelerometer is actually witnessing that tiny motion. And we can use that to just make a simple Wiener filter and subtract that noise out of the data, which is what you see here. However, I do want you to notice that one of these camera shutter glitches, and we know this because of the accelerometer, falls right on top of the precise points in the signal where you would expect precession to be most apparent. So we did what we thought was a conservative approach where we only subtracted the power that we could witness with the accelerometer. We didn't model it with wavelets. However, another study, a follow-up study, did. They did model the power incoherently with wavelets. So what you're looking at here, this is the inferred source property estimation, including the mass ratio and the effective spin and the processing spin over here. This is the key parameter in question. So here is the unmitigated data and the data that was mitigated just with the accelerometer with that simple Wiener filter. So these are the black and pink plots here. However, when you do this incoherent modeling with the wavelet, you capture more power that you're able to subtract. And now here they're getting posteriors that are more consistent with something that's not processing. So that goes away completely if you capture more power that could be potentially associated with that glitch. And I will also note that also if you exclude looking at this, any frequencies below the frequency of the glitch at all, you also get something that's more consistent with something that's not processing. So the importance of paying attention to your data for those of you who are doing data analysis. And here we come back to the need for automation. So I think I mentioned it took us months and months to generate subtraction for just one candidate. Some of them took weeks, but all of them took a lot of time. And now we're getting signals about once every other day, or every few days. So it's not feasible for us to do that anymore. So here we come to the need for automation. We expect on the order of 100 candidates, so maybe 150, 160 candidates from O4. For OR5, we're expecting more than 800 candidates. So with a higher detection rate and a longer observing run, the danger here now is that if we have automated systems that only flag problems, that you're going to pass candidates that have glitches in them, and then you might find modifications of GR, you might find something in the data that's more related to the noise than the astrophysical signal that you're seeing. So here's an example of the automation that we currently have in place. So this is called the data quality report. And you can read more in this paper by Rita et al. So here we've got for each one of the detectors in our network, we've got an overall status. Is there a problem or is there not a problem? And whether or not it's observing. And each one of these tasks is supposed to measure in a different way the likelihood that there's a glitch present. And we have a number of different tools contributing to this. Also more than you can find there that operate on slightly different latencies. So something that I want to highlight is an exciting project that's led by a student who was working with UBC for the summer, Sophia Alvarez, who's now a grad student at MIT. So she developed this algorithm called Gravity-SPI Neural Net Decision Tree, or GSPI Net Tree, that takes this Gravity-SPI classification algorithm that we were looking at for glitches and repurposes it to try and differentiate between glitches and signals. So here, the goal is to identify any part of a glitch that may be present near a candidate, and eventually what we want to do is actually draw that time frequency box around it, automate that subtraction. This is the overall end goal. And a key element of this algorithm is breaking the problem up into different mass ranges because they have extremely different morphologies. So the low mass convolutional neural net, so this will have longer duration signals, and it will also, we expect, be more affected by the glitches that have similar morphologies, so similar long duration morphologies. And similarly for high mass, and what we've said is extremely high mass, we expect this to be confused more by the very short duration kinds of glitches. So here's some examples just to give you a sense of the different morphologies. So we have, for example, 30 total solar mass system on the top, and then what we would said was a high mass system, it's 182 solar masses here, and then roughly about 119, and then 283. And on the right, you can see different examples of glitch classes that are included in the classifier. So some of them, like Spectry, that have this longer duration feature, and they're paired with the low mass classifier. Some of them, like Tomties and low frequency blips, are paired with the high mass classifier to try to give that classifier more distinguishing power. And the workflow, I'll walk you through very quickly. So let's say we've got a candidate event. That candidate event is dropped in our database. A public alert will go out if it's a significant candidate. And then GravitySpy NetTree, GSpy NetTree, is going to fetch that data. It's going to generate a series of spectrograms at different durations. And this is really important for capturing the different ways the candidates can manifest at time and frequency, some of them being much longer than others. And the next part is the decision tree. So is the mass of the candidate lower or greater than 50 solar masses, which is what we found is roughly a good threshold for splitting the problem up. If it's yes, it goes to the low mass. If no, it goes to the high mass. And then there's a second decision tree happening where if it's extremely high mass, which is unlikely that we'll see them in this run, but we're robust to them anyhow, we've got an additional projection that helps us build a feature set that has good distinguishing power. And then finally, this result of whichever classifier that was that it ran with is sent to the data quality report. And something else that we've been thinking about is how do you deal with cases where you have a glitch and a signal? You don't want a classifier that's only ever going to tell you either or, is this a glitch or a signal? This being one of our most famous examples. Has anybody seen this pop before? A few of you, yeah, okay. So this is actually the first detection of gravitational waves from a neutron star merger. And this is the raw data from LIGO Livingston at the time. And you see the screaming loud glitch roughly about a second before the merger. So we want to be robust to cases like this. We want to make sure that we can flag both of the elements that are present in this kind of a feature set. So what Sophia did was she adopted this multi-label classification. So we move away from binary classification. Is it a glitch or is it not a glitch? Towards multi-class, which gives me more power to distinguish between different elements that might be in the image, where the classifier may do fairly well with both dog and plant, but not robust for either or. And then multi-label, finally, I've got a classifier that can tell me with some confidence that I have both of those elements in my image. So Sophia has now implemented this into GSpy NetTree. So now we have a classifier that can tell us, yes, there is a Tomty here with high confidence. There's also what we would call a chirp or a gravitational wave signal present in the data. So that was a big advance that was just written up in a paper that she submitted to CQG that just got accepted last week. And the performance and accuracy is very good. Just about 98-99% accuracy and recall, which is particularly important if you want to make sure that you're finding all examples of those glitches in all the different classes. And remember, there are different sets of classes depending on which classifier. All right, and I'll show you an example of where it's adding to the menagerie of tools that we're already using for automation of validating these candidate events. So here's an example that's taken from Virgo data. So this is a spectrogram of the Virgo data. GSpy NetTree issues with high confidence that this is light scattering. There's light scattering present in the data. And the older tools that we have that are meant to identify issues of data quality and gravitational wave data don't do a good job with this. So here in this red box, this is the region of the candidates that this tool is looking at. However, it fails to find this as an anomaly because, as we saw before, light scattering repeats. Light scattering happens over and over again, which pollutes the spectrum of the data at the time. So this tool is blind, essentially, to something that's occurring once every other second, whereas GSPINet tree gives us that robustness. Something else that's really cool that I want to mention is that we've just partnered with company Veritree that verifies that trees have been planted and that ecosystems are being rehabilitated in those regions. They have partnered with Nico Lagoche, who we mentioned earlier, to help them with their algorithm that will intake images of trees, count the trees, and tell you whether they're dead or alive. So you can see here that they've already had a team of computer scientists write the algorithm. It does really well when the image quality is high and the trees are distinct. You may notice if you've been reading this, the confidence labels here, it does not do well either in counting trees or in identifying trees. So they've turned to the astrophysicists who have been thinking about data quality to help them improve this. So this is a really exciting project, and we're looking forward to applying what Nico learns through Veritree to also write our own program that will segment this data and tell us where in time and frequency those glitches are so that we can fully automate the subtraction. All right, what else is next? So we've got a few other irons in the fire in terms of differentiating between signals and noise. I'll just briefly mention another cool project that Neev Shah did. So he was another summer student who worked with us at UBC, who also just had a paper. Actually, this was also just recently accepted last week. I'll give that an update. So what he's done here is he's taken posterior distributions, which we get for free in terms of analyzing all of the events in our catalog, and he breaks them down into the different components and compares them to what you get if you run parameter estimation on a set of glitches. So we're using Bayesian parameter estimation of source properties as our feature sets, and he fed this into a random forest and had really, really good performance, especially in identifying glitches. So this is something that we're thinking about reincorporating as part of the weighting schematic for a gravitational wave search. All right, and I'll also highlight, so there's a pan-Canadian network that's growing, that's thinking about machine learning in different aspects. So from gravitational wave astrophysics to transient searches, which is something Renee Holczek at UT is working on. And we've also got partnerships with neuroscientists who are at the University of Laval, who actually face very similar challenges in terms of image classification and image analysis. All right, so I also wanted to, I see that I'm already getting close to the end of the hour. So we'll take a brief tour of this. So here's a sense of what else we might detect with current detectors. So this is the coverage of accurate templates. So how confident are we that we know exactly what the signal will look like? And here's how long we'd expect that source to stay in the band of the detector if we could observe for an infinitely long time. So we have already detected examples of sources of compact binary coalescences, CBCs. Arguably, we have also detected an intermediate mass black hole. And then down here towards the more unmodeled side, we have not yet made confident detections here. We also have not yet seen any long duration sources. So for example, continuous waves or stochastic background with ground-based detectors. But as our detectors are getting more sensitive, as they're improving, so are our prospects for making this first galactic detection of continuous waves. So I'm going to tell you as much as I have time to about a study that a PhD student at UBC is leading. So this is Alan Mee, and I have borrowed Alan's beautiful slides from 2 talks that he's previously given. So this is outside of my own expertise, but it's a really exciting project that I've been learning a lot about through Alan. So we'll go on this journey together. So continuous waves, unlike transient gravitational waves. So for transient gravitational waves, the frequency of that gravitational wave is going up as the binary is rapidly getting closer together. Here, the gravitational wave signal is going to be going down. So we've got some kind of an isolated source. Maybe this is a neutron star with a little, we call it a mountain, but some kind of deformity that its crust can support. This could also be maybe R modes or some kind of internal sloshing that's giving it some asymmetry as it spins. But we've got some isolated system with some asymmetry, and as it spins, it's losing energy and actually spinning down. So that frequency very slowly is going to go down over time. And we expect these, even as close to us as we know some neutron stars are in our own galaxy, we expect this signal to be very, very small. So here's an example of realistic detector noise. It's a strain amplitude versus time. And if you zoom way in here, you can see this extremely weak sinusoidal signal. And I'll also emphasize that a realistic signal would actually be much weaker than what we're looking at here.
So for how many radio pulsars can you now set an upward bound on the gravity wave signal that corresponds to a negligible impact on spin down?
That's a really good
I
question.
mean, you do that with crab, can't you?
Yes, the crab is a favorite. And actually, interestingly, so the crab has been spinning at about 60 hertz. We mentioned this earlier as a frequency of interest, very noisy frequency for us. It's spun down enough that it's starting to be easier for us to analyze the crab. So the collaboration selects highly stable millisecond pulsars. So there's a lot of parameter space that I think is left unexplored by our papers to.
But is that still the only one for which you can say it's not spinning down by gravity wave?
Well, I think we
Primarily.
haven't said it's not spinning down at all. I think we've said that it must be spinning down below. It must be emitting energy below some level. That's how I refer to it.
I thought I'd seen a claim that was non-time. You could actually rule out a dominant contribution.
Yeah, I think with gravitational waves, we can't rule out that it's not spinning down at all. We can only set that upper limit. But it's the crab and dozens of other sources that the collaboration is targeted. Yeah, great question. Anything else in anybody's mind?
Well, I guess the other thing that was coming to mind, for a black hole line is about 100 solar masses. How does the detection distance scale with mass? So it's rapidly dropping, as I understand, as you go up in mass because the frequencies are getting lower. Is there a rough scaling that one can envisage
I
between
can
those
give
two?
you some benchmarks. So let's say for a neutron star source that's about 1.4 solar masses, about 40 megaparsecs would get you, well, let's say maybe for an SNR of 10, so the one that we did detect was about 20, so let's say on the order 80 to 100 megaparsecs for a neutron star. A binary black hole system that's maybe 100 total solar masses, an equivalent SNR would be gigaparsecs away.
Right, but I'm wondering, you brought up intermediate mass black holes as you go to 200, 300. I mean, there will be, if you have a 300 solar mass binary in Andromeda, you will see it. I mean, if it's merging in Andromeda, right?
Unfortunately, no. So above a certain mass, so those black holes are going to merge at a
But
lower
even bring
frequency.
down, there's no high order contribution that you would.
There may be a higher order contribution, but it won't rise above the level of what we call our seismic wall. This is the low frequency end of our spectrum that's very noisy. The Earth is very noisy, humans are very noisy.
But, okay, so, 200 will be.
200 is plausible. I agree with you.
I see.
200 is
Okay.
plausible.
So there's a wall really then about 200 to 300 where really cut out. Yeah,
Lisa, however, may be a different story.
of course.
Yeah, great question. All right, so let's see. I may just give you we'll kind of glide through the last few slides, the last 10 or so slides, and the last 5 minutes or so. So something that I find really interesting about this project, so thinking about pulsars that are spinning down, most of the major studies assume that the spin down is roughly constant over a long period of time, so that you can have a signal that's fully described by some initial frequency and then some frequency derivative. And that's what you need to describe it in addition to the position that it's in the sky. And once you know that, you sort of know everything that there is to know about how to find that source in the sky. However, physically, we do expect that there are some mechanisms that could perturb this frequency that would not cause it to follow this very regular derivative in frequency. So for example, if it's accreting, you might expect to see some kind of a semi-stochastic wandering in the rate of the spin over time. If it's in a binary, you're going to get some interesting modulations to the frequency. You might also potentially see a glitch in the pulsar that would put an anomaly in your frequency data. So essentially what we want to build into the way that we search for these sources is some kind of robustness to these potential anomalies in the frequency. And it's important for any kind of search that we're going to do, however it's evolving in frequency over time, is to think about the impact of where it is in the sky and how that affects our data. So for example, here's a very, very artificially loud simulated source in the data. So this is time in days versus frequency. You can see this very large modulation. So this happens to be 365 days, I'll tell you, just to give you a sense of what's going on here. But if I zoomed in really closely here, you also see this smaller modulation that's got a 24-hour cadence. And if I demodulate both of those, then what I'd be left with is a signal that's going very slowly down in frequency. And just to give you a sense, this doesn't even go 1 hertz, to give you a sense of how slowly this is moving. And then if I do a spin down demodulation, now I've got this nice stable starting frequency. So this is my F and F dot. So this is a huge number of parameters to search over. So I've got 2 parameters that describe where it is in the sky, and then I've got 2 more parameters that describe what physically the source is doing. So the computational cost of this is quite large, and for that reason, often we don't do a fully coherent search. So this is where you try and integrate your signal to noise ratio over the entire observing period, which would give you a nice strong peak. So this is frequency, and this is detection statistic. You get a very strong peak if you could do this. Often this is completely infeasible to do for computational reasons. So usually the method then is to do a semi-coherent search. So you divide your data into time segments and then you sum them incoherently, which gives you a less significant peak, but it's possible to do this in a feasible amount of time. So this is where we're coming into the search. This is the framework that we have, this semi-coherent method that, again, we want to be robust to something that's potentially changing in frequency. So here is data where there is an injected simulated spin wandering signal, and our job now is to find it. So we've got some number of frequency bins here and Q, some number of time segments, and this is the number of segments we've broken our semi-coherent search up into. And this is now, again, a huge number of possible paths. So computationally, we really want to avoid searching all of these paths if we can. It's quite impractical to brute force it. So something that Alan and other collaborators came up with is leveraging this Viterbi algorithm in hidden Markov models. So the idea of a hidden Markov model, if you haven't worked with one, you have some observed states. So that's the strain data for us as a function of time. And then you've got some hidden state, that's what you're interested in, that's driving that observed data. So for us, this is the frequency that this pulsar is spinning at, or neutron star is spinning at. And then we can describe this with a hidden Markov model by making some transition probability between our states. So for us, we're going to limit this neutron star to 1 frequency bin over. It can stay at the same frequency bin, or it can go 1 above or below. That's going to be what we let our sources do. And then you also have the likelihood that this observed state, this frequency, would produce the data that you observe. So with those 2 parameters, you can construct this global maximum of the probability, and you also introduce them this set of prior knowledge that you have about the system, which we usually keep uniform since we don't usually generally know inherently what the frequency of the signal is going to be in an eyes wide open approach if we're not targeting the crab, let's say. All right, so here's an example. So let's say we've got some hot pixel, and that pixel is, let's say, here. And again, we can go forward and then up or down in frequency bin. And then let's say, all right, at the next stage, we're only paying attention to the pixels that seem likely. So the power of the Viterbi algorithm is you're only paying attention to the survivors. You're throwing everything else out, you're culling it, and that saves you a lot of computing power. So now here, again, we've got sort of two survivors. They're each going to do their own branches. And then again here, we're only keeping the survivors until finally we're working our way through and we've got some best overall possible path. And this is much more computationally friendly to arrive at this result. And here's just an example. So again, here we've got the same data with a simulated spin wandering signal. This is frequency versus time. So with my human eyes, I have no idea where this is. It's buried somewhere in my data. And Viterbi, if I use Viterbi to find the most likely path, now if I use the Viterbi power as my detection statistic, I've got some spike that's rising over my noise, and it's even broad in frequency. So this is telling me that it's capturing the wandering around in frequency that my signal is doing. So we don't expect the Viterbi algorithm to capture exactly what the path is. It just needs to get close enough that we can get that signal to rise above the noise. And Alan added this really nice overview of all the different ways that the collaboration is currently deploying the Viterbi algorithm. So this is not the first study to leverage Viterbi. We've also, especially in the arena of continuous wave sources, had previous applications. And then let's see, I see we're on the hour. I'll just quickly tell you about this new paper that's now up on the archive, which is this end-to-end search that Alan has done following up this all-sky, all-frequency search. So this is a stochastic search that returns these hot pixels in the sky. So these are candidate sources that we know the sky location, and we know roughly what the frequency of the candidate is. And so this is the result of the search that was published by the collaboration a couple years ago. Each one of the pink dots that you see here, these are background events. Each one of the blue dots is the foreground, and this yellow line is tracing the 99th percentile of all the background events. So we can see that there's not really an outlier that rises significantly above the background. However, all the teal circles, these are foreground events that were flagged for follow-up, which is what Alan's search is doing. So they're taking those hot pixels. They're not significant enough on their own. However, if you take the starting point of that sky location and that initial frequency, now we can leverage this Viterbi method to search for something that's robust, again, to this interesting physics of these neutron stars behaving in ways that are not going to result in this consistent long-term spin down. All right, and I'll give you a sense of what the search looks like. So this is a true injected path that we see here in blue. And this is Alan's algorithm that's finding an optimal path here in the green dashed line. And the way that he deployed this to the outliers from the all-sky, all-frequency search is by breaking the sky pixel from that search down into templates. So these are broken down into frequency and frequency derivative, F and F dots, and then dividing the O4 data into 24-hour segments. So this is the incoherent part of our search, and then leveraging this algorithm for each one of those templates, which is going to give us actually a really big trials factor. Every candidate's going to have hundreds or thousands of templates. And this is how he populated each one of these candidates. So this is the sky pixel that you see here in the diamonds. Each one of these green dots is a possible exact sky location that Alan has targeted, and each one of those green grid dots is then also going to be populated with F and F dot templates as a starting point. And what Alan has done is run the Viterbi algorithm on each one of those templates, and then templates within templates, hierarchical templates, and estimated the background of this approach by essentially repeating the same process outside of this target candidate sky grid. So these are the off-target points that are used to generate this histogram that you see here in blue. So this is the background with a likelihood fit here. And then you can construct a threshold for significance using this background. So empirically, you can do this if you are targeting some particular false alarm ring for an individual candidate and template. So here again, we take a penalty for the trials factor. So this is significantly removed from our background for one individual place in the sky, and also F and F dot. So we can set this to be equivalent to one particular candidate having a false alarm rate of roughly 5%. And here's the result of the search. So these are all foreground events. Here's the same threshold that we just saw that we set empirically. One of these candidates was vetoed as being either a known line, or the signal goes away if you only look at one detector. And there are only a few candidates. None of them are really rising enough above the threshold of detection that we feel really confident saying that we've detected the first galactic source of gravitational waves. They're all very marginal, but this is a really nice demonstration, I think, of the methods. And again, we're very excited about this O4 data, which is significantly more sensitive than the data we searched on. All right, so I will leave you with this. If any of this you find exciting, there's a lot happening in Canada to get involved with. So there's, of course, the group of affiliates, which is Tuesdays at noon. There's the Open Science Center, which we drew a lot of our data from. If you're interested in LISA, we gave some shout outs to LISA earlier. There's some really nice talks about LISA efforts within Canada that are up on YouTube. There's also Cosmic Explorer, which Phil can tell you a lot more about, the LISA Consortium and the LSC. So feel free to chat about any of that if you find it interesting. I also want to flash up an advertisement for a meeting that we're hosting at UBC. So this is called Dawn 7. This is a series of meetings that's supposed to be community planning. So this is users of gravitational wave data, builders of gravitational wave detectors, people who are generally interested in gravitational wave astrophysics, focused on ground-based detectors. So this is going to be particularly focused on the next upgrade to existing infrastructure of the advanced LIGO detectors. We're also interested in atomic interferometers, European plans, and of course the users, the astronomers and multi-messenger astrophysicists. So I highly encourage you to come if you're interested. It's June 12th and 13th. And then I think I will leave you here. Thank you very much.
We're a bit past the hour, but is there a quick question?
So what are the limits on measuring light speeds relative to the gravity output that would need to be produced to counterbalance the accretion torque? Because there's this puzzle about the non-spinning breakup, right? So it's probably a magnetic torque, but if it weren't a magnetic torque and it was gravity waves, then there's a certain amplitude of the waves that is implied. And how does that compare with the actual upper bounds that are now, or maybe detections?
That is an excellent question that I do not know the answer to, but I think I could probably point you to some papers.
Yeah. Okay. Thank you.
I think LFSK is for giving credits.
What? I don't.
I mean, like the gravity wave to still down.
Yeah, that's true.
Because they're far.
But still, it's a question.
Okay. Okay.
You know, they're close by, right? Really close by.
Well, not in the, I guess not in the gravity wave. Like not.
They're close by, but there's not a lot in that happening in this quadrupole moment.
Yeah.
These are mountains that are on the scale of centimeters, just for scale.
Okay, thank you.
Yeah, so let's carry on the discussion in the lounge upstairs.
Sure.
But thank you again, Jess, for the great
Thanks,
talk.
everyone.
Hi, Jess, great to have you.
Yes, good to see you.
So, you see there's an embarrassment of riches today.
Yes, I saw.
So I have to go to this physics thing. With
Please, yes.
Same,
That looks really cool.
Same territory, right?
Yeah.
I mean, it's great. Everybody's got you well organized.
Oh, yes. Phil has been excellent. Thank you very much.
Yeah, probably.
That's great.
Good to see you.
Yeah, really interesting, the pattern matching and the new